We're continuing on here, chapter 2. Last time we got into sort of dimensional analysis and conversion factors and how to set up the problems. So as we've been talking about again, um, we always want to use any type of equality that we have. Will give us again our two sort of conversion factors to use, which as we talked about are really just fractions. And as I mentioned before, and a number of times again in chemistry, sort of how they want you to show your work is to do, in most cases, a dimensional analysis approach, which is really just units canceling. And when we do dimensional analysis, again, we just want to go opposite to cancel the units that we don't want. And you can just think of it really as a fraction on top or on bottom. So again, if we had 32.5 inches, and we want to know how many feet that was, we would start with our 32.5 inches. You don't have to write it like this, but if it helps you just to visualize sort of where the units are, you could kind of turn it into a fraction by putting it over 1, or you could obviously just leave it as 32.5 inches and understand that if you just have one number by itself, the units there are on top. So whichever way is sort of easier for you. We do want to cancel out the inches. So the only thing we have to remember when we're doing this is opposite location will cancel out those units. And that again makes our selection of our sort of conversion factor pretty simple. That's the one where our inches are in the bottom. So we're going to go 12 inches is 1 foot. Remember as well, there's really only two things that we do in terms of math when we're doing dimensional analysis. We multiply or divide, and anything on top always gets multiplied. Anything on the bottom, it always gets divided. So those are really the only two math things that you do in most dimensional analysis. The reason this works is, again, we're basically dividing inches by inches, which basically turns it into a 1, just like if you divided 2 divided by 2 would equal 1, and they cancel out. So in this case, we have 32.5, obviously, here, divided by 12. We'll give you something on your calculator, once again, as like 2.70833, a bunch of threes going on. And the only units that are left are feet. Remember that when we do dimensional analysis, one of the nice things as well is you're only multiplying and dividing. So when it comes to your final answer, you should always be looking at significant figures. So that kind of also narrows down, what we should end up with in terms of our answer. Now, when we talk about sort of conversion factors or equalities, remember there are some that are considered exact numbers, which a lot of them are, and there are some where you do have to look at the conversion factor to worry about the significant figures. So remember that if it is going to be considered an exact number, typically that is your metric to metric conversion. So those, if you're using any type of metric to metric conversion, it will consider an exact number. You don't have to worry about it in terms of the significant figures. If you're doing sort of a English to English or US to US, that is also always going to be considered an exact number, so you don't have to worry about it. It is only when you cross over and you go metric to English or vice versa, English to metric, you do have to worry about sig figs. And there are a couple of exceptions. The two notable ones that you're responsible to know is, again, in that situation, 1 inch is 2.54 centimeters. Once again, that is something you should know. And also here, 1 pound, 453.6 grams. So except for those, anything where you kind of cross over, you do have to kind of look at the significant figures in that conversion factor. You would, in most cases, have a conversion factor usually that has like 1 as one of the numbers there and another number that obviously has a couple of significant figures or so. You would look at the number that is not 1 usually in that conversion factor. So when we look at this here, this is definitely an exact number conversion factor. Again, we don't have to worry about it. So we are going to default back to our original number, which has 3 significant figures, and that's going to take us out to here. We would look at the 8, and we would round up in this case to 2.71 feet. First off, any questions on that? Benefits of dimensional analysis, besides the fact that that is how they want you to show your work here in chemistry as you go through your different chemistry classes. It also, as you'll see, if you continue to sort of use it, can be very helpful, especially when you get the formulas as well. Sometimes by just taking a dimensional analysis approach rather than maybe trying to remember a formula and just getting rid of the units you don't need and keeping the units you do need, it will actually a lot of times kind of do the rearranging of the formula for you without you having to worry about it. And it takes care of the math of it because all you have to remember is multiply the top, divide the bottom. So a lot of times you may not even need an actual formula that you maybe learned if you just kind of look at it more of a dimensional analysis approach and kind of worry about the units and getting rid of what you don't want and keeping what you do want. Any questions on any of that there? Obviously here we only did one step, but if we had multiple steps, you could just continue down, keeping units on top and bottom and hopefully cancel out correctly. All right, so let's just take a look at a couple more conversions before we finish up this chapter. But why don't you try this? Let's say you were driving 72.5 miles per hour, and we want to know what that would be in feet per second. And as with one of these conversions or equalities, you should know 1 mile is 5,280 feet. That is definitely one you should know. So once you do that conversion, why don't you also do, let's say we had 0.425 inches cubed. What would that be in centimeters cubed? And again, another one that we just talked about there, you should know 1 inch is 2.54 centimeters. All right, so take a few moments here, work them out, dimensional analysis approach. I will as well, because I just made them up. Hopefully we'll end up with the same answer. Look, so again here, we actually have 2 units that we need to convert. We really need to convert miles to feet and hours to seconds. So again, we definitely want to set this up, dimensional analysis, and keep those units in the proper location and know which one's on top and which one's on the bottom. So here, that is where we would start, 72.5 miles over hours. And that's exactly how you should write it. So you could clearly see which one's on top and which one's on the bottom. Probably not the, miles / hours, 72.5. That's probably not a good move because you will lose track. A lot of people do lose track of which one's where. So again, you really want to kind of set it up so it is very, very clear. So it doesn't really matter which one you kind of tackle first. I'll do the miles obviously here to feet. So by having it set up like that, once again, opposites cancel. So miles are on top. That means when I come to my equality here, I'm going to put miles in the opposite location, which is on the bottom, and feet up on top. If I stop the calculation right at this point, miles will cancel, and I will be in units of feet per hour at this point. Yeah. This is really important to understand again that hours are on the bottom there because it makes my next conversion hopefully going to be correct here. Now, you could do it a couple different ways. You obviously could do it, and hopefully you know this, right? There are, I think, 60 seconds in a minute, right? 60 minutes in an hour. So again, you can use those conversion factors. You could also use, obviously there's 3,600 seconds in an hour, so you could use that as well if you wanted to. So again, just to do it this way, and I'm going to actually erase those because I think I'm going to run right into them. But we will take those conversions and continue on. So again, by setting it up like this, I clearly see hours are on the bottom, so to get rid of them, hours will go up on top, and 1 hour will be 60 minutes. Hours on the bottom and top will cancel. At this point, I will be in units of feet per minute, which is close to what I want, but I do want to get it to seconds. Again, by setting it up like this, I can see clearly minutes are on the bottom, which means to get rid of them, I need to put minutes up on top on my last conversion. And in 1 minute, there is 60 seconds. Minutes will cancel. I now have feet on top, seconds on the bottom, which are the units that I am looking for in this particular case. First off, any question on the setup there? This is what you do need to show. You do need to show like that for your own good. I can't tell you again how many people I've seen over the years at this point would be multiplying by the 60s at the end there because they don't know where the hour is and they're not sure if they're supposed to multiply, not sure they're supposed to divide and stuff like that. So again, if you keep it really clear in your setup, which you should do, it should make it really easy. Math-wise, also really easy because I know everything on top here all the way across gets multiplied and everything on the bottom gets divided. So there's no mystery of what I need to do math here. So when we go to put this in, you also want to be careful putting it into your calculator. As we talked about previously, you're going to go 72.5. We're going to multiply it by 5280. At that point, there's really nothing else to multiply up on top. You should probably hit equals on your calculator. Now I got a couple of numbers on the bottom I need to divide by, which are the 60s. I'm going to divide by the 60, and then I'm going to hit equals. Then I'm going to divide by the 60 again on the bottom and hit equals, and that should give you the right answer. So again, try not to put too much in your calculator at once. Otherwise, you may end up with the wrong answer. And on your calculator here, it is going to give you something that looks like this, maybe a couple extra threes I didn't write, but something in that ballpark. Now we want to look at sig figs, right? So exact number, not going to worry about it. Exact, not going to worry about it. Exact, really don't have to worry about it. So coming back here, we got 3 significant figures. That means we should end up right there at the 6. The rest are 3s, so we'll end up at 106 feet per second as our answer. Any questions on that? So again, when you're dividing that bottom, you got multiple numbers, hit the equal in between each number and divide them separately. Always will get the right answer in that case, rather than trying to put them all in at once. Any questions on that one? All right, last one here, 0.425 cubic inches, and we want centimeters. So clearly here we could use this equality. So I'm going to start with my number here, 0.425 cubic inches. Once again, the cubic inches are on top. So I'm going to use my conversion here, and that is going to be an inch on the bottom, 2.54 centimeters up on top. By the way, did I properly convert it at this point? Did I get rid of the inches cubed? I did not. I actually only did 1, right? Technically speaking, you need to do this conversion not once, not twice, but you need to do it 3 times. Yeah. And inches times inches times inches gives you cubic inches, which will cancel all those out. And centimeters times centimeters times centimeters will give you your cubic centimeters, which you are looking for. And in this case, we would multiply what's on top, divide what's on the bottom, which there's not much there. So we're going to go 0.425 times 2.54 times 2.54 times 2.54. And that's going to get me, it looks like on my calculator here, 6.9645022. That's all the digits on my calculator. Cubic centimeters, We do need to look at sig figs. Although this is a metric to English conversion, it is considered an exact conversion, which means we don't have to worry about it. Once again, coming back to our original number, which in a lot of cases you'll do, that's 3. Going to take us to the 6 here, and that's going to give us 6.96 cubic centimeters in this case. First off, any questions on that there? Yes, I'm pretty sure I'm going to. Your question is what I was just about to say, but go ahead, ask it. That's exactly what I was just going to talk about. And the answer is absolutely. Your question is, I think it was 0.425, I think, right? And that was inches cubed. So your question is, can you do 1 inch, 2.54 centimeters, and cube it like that? Absolutely. There's nothing wrong with that. My experience, though, is when students do that, they manage to cube the units, but never the number. Yeah. So it's a very common error when people do that, and there's nothing wrong with that. It's perfectly fine setup. You do just need to remember to do it 3 times, right? And it's a super common error. People set it up that way and just like do the number once and stuff like that. So my recommendation, maybe just write it out so visually you see it like, oh, I got to do it like 3 times, but there's really nothing wrong with that setup. But super common error people make. Other questions? All right. Last thing we're going to talk about in this chapter then is density. Density can be defined, as we talked about in lab on Monday, as the mass of a substance over its volume. Differences in density, as we talked about, for example, with water, will determine whether or not something will sink or float. Something is more dense than water, it will sink. If it's less dense than water, it will float. Just in general, if you ever need the density of liquid water and it's not given to you, but you feel like you need it in a problem, 1 gram per milliliter is typically the value that you could use. And that's a number you should kind of put in the memory bank as well. It pops up a lot. And again, it's not oftentimes given to you in problems. They just kind of assume you're going to go with that number. Now, a side note to that, that we might see in a later experiment, but a side note to that is that density actually does change with temperature. So as the temperature changes, so does the density. So water's density is not always 1 gram per milliliter, even though that's usually the number that you will kind of always use. It actually does change with temperature. So just keep that in mind. Density will change with temperature, but for 99.99% of the time, if you kind of need a density value to use for liquid water, 1 gram per milliliter is pretty much the one you should roll with as you go with it. Now, the density is typically things in their solid state are usually a lot more dense than, say, in their liquid state. And one exception actually is water, right? So water in its sort of liquid state is actually more dense than in its solid state, which is ice. When we put ice in our drink, it ends up at the top, right? It floats to the top. And again, that's because it is actually less dense. So ice has a density like 0.9 rather than 1. And what happens when you get ice, as we'll talk about in a later chapter as well, as those water molecules basically come together and bond with each other, they create a big open space. They don't have enough energy to really get super close to each other. So they can only get so close to each other. It creates a lot of open volume within an ice crystal. And because density, as we will see, is mass over volume, the density of ice is actually less than liquid water because of that. It kind of bloated with kind of this empty volume between the different water molecules as they go in the solid state. That's because in the liquid state, they actually have a little bit more energy, so they can actually get closer to one another. But as they get into that solid state, they kind of lose some of that energy, and there's these big open sort of spaces between the water molecules. As we talked about last time, you could calculate the density as the mass over volume. It is a formula you do need to know, obviously. So you can rearrange it. Density is mass divided by volume. Volume is mass divided by density, and mass is volume times density. Sometimes people like the DMV triangle. Density is mass over volume, mass is volume times density, and volume is mass over density. So sometimes people like to remember it that way. And typical units, as we talked about for density, is grams per milliliter or grams per cubic centimeter. And that's typically what you see with solids and liquids. Again, a reminder that 1 cubic centimeter is the same as 1 milliliter. So again, they are the same. For gases, typically density is given to you in grams per liter. We won't deal too much with density of gases in here, but when you go to 1A, you'll do some calculations, especially in the gas chapter. And typically gases densities are given in grams per liter. Most of the time we will see kind of these units here. And typically when you calculate the density, the number stays with the grams part, and it's always 1 milliliter or 1 cubic centimeter, sort of the bottom part of it. All right, so why don't you give it a go here? A block has a volume of 25.3 cubic centimeters and a mass of 21.7 grams. What is the density? Which is our mass divided by our volume. And obviously, again, this is a volume, 25.3 cubic centimeters. We have a mass that's 21.7 grams. So clear, you could check both of those off, and all we have to do really is just plug it into here. And that's going to give us here 21.7 grams divided by 25.3 cubic centimeters. And on your calculator, that's going to give you 0.8577071. The units do not cancel, so number keeps the grams over 1 cubic centimeter. Clearly, we still need to look at sig figs here, so we are dividing in this case. So we're looking at the number of significant figures. So we have 3 sig figs up there on top. We got 3 sig figs on the bottom, which means we should end up at 3 significant figures here. And that's going to get us to 0.85. We do need to round up in this case, 8 grams per cubic centimeter. Questions? Yeah. You can. There's nothing wrong with that. It's okay. You can technically do that and just write the number there. It should be okay. Yeah. Other questions? All right. Now, when we get the volume of a substance, there's usually a few different ways we could do that we've kind of talked about and we've kind of done in lab as well. Obviously, here you can, if you want a volume, just simply take a volume reading. If you have something that's like a cube, you could do the length times the width times the height, right, and get you a volume. If again, like you did with those rulers, if they're all in centimeters, going to give you cubic centimeters. Also, like we did in the lab on Monday, a very, very common way to get the volume of an object, especially a solid object, and when you're dealing with density, is volume by displacement. So a solid object will displace something like a liquid like water equal to its own volume. So basically here, before she dives in the bucket, we have an initial volume reading. When she goes for a swim, she's going to displace that water, and we're going to end up with a final volume reading right there. And as we talked about, if you essentially take the difference between the final volume and the initial volume, that will give you the volume of the object that you're looking for. So this is a very common way to figure out the volume of an object, as you did with the stopper. You just need a little bit of water, take an initial reading, drop it in there, take another reading, and you can get the volume in that fashion. Hopefully she's able to get out, and that's actually stairs, where she can hold her breath a really long time, hopefully. All right, let's see. All right, so why don't you give that a go? This one, a student fills a graduated cylinder to 25 milliliters with a liquid. She drops a solid into it. The volume of the graduated cylinder goes to 33.9 milliliters, and the mass of the solid is 63.5. What is grams? What is the density? So take a few moments, see what you come up with. Okay, so let's take a look. So it's kind of situation like we did in lab. So you got a graduated cylinder professionally non-drawn there. And we got some liquid in there that's initially at 25.0 milliliters. We got this solid here that has a mass of 33, not that, 63, 63.5 grams. We're going to toss that in there. They didn't have quality control there. And we pop that in there. And we're going to end up with a final volume here of 33.9 milliliters. So once again, we're looking for our density. And we can find that again by the difference, or get the volume by the difference between our initial and final volume. Density again is our mass over volume. We obviously have our mass right there. So to get our volume of our object going to be the final volume minus the initial, which in this case is 33.9 milliliters minus 25 milliliters. And that is going to get us here 8.9 milliliters. We now have the volume, we have the mass, so we could go in here and do our calculation, 63.5 grams divided by our 8.9 milliliters. So we take our 63.5 divided by 8.9, gonna get us a 7.1348 and a bunch of numbers there. I'll just stop right there. Grams per milliliter. Here we do again need to look at our calculation, and this has 3 significant figures up on top. This has 2 significant figures, which means we should end up at 7.1 grams per milliliter as our density. The final answer is really determined by what calculation in this case? It's determined by the subtraction calculation, right? That's what you did first. And when we do this calculation, we're actually not looking at significant figures, right? We are looking at decimal places, and we need to go to 1 decimal place since they both have 1 decimal place. That is what we did. So we went to 1 decimal place. Even though it has 1 decimal place, that number ends up with 2 significant figures, which plays a pretty big role in our final calculation, yeah? So again, you do want to make sure you keep track of it all the way through your calculation, because it could actually really be calculation you did at the beginning that could actually affect where you should take your answer to at the end. Yeah, so you just want to kind of keep track of it. Any questions on that there? All right, here's a table from your book, some density of some common substances. Again, you can see the density of water is 1 gram per milliliter. Once again, they do want you to know that number. But again, it does change with temperature, as we talked about, but that's a pretty safe number to use if you ever need to use it for liquid water. You can see everything below that will be more dense than it, and it should sink in it. Anything below it will be less dense. If you have some liquids that have different densities and you put them like in a tube or a graduated cylinder, they will separate out, right, based on density. The most dense solution would be to the bottom, right? Less dense would be to the top, right? And if you put something like solid in there and it stops right about there, that means that that solid is more dense than what's above it, right? And less dense than what's below it, right? And it will stop there. Any questions on that there? It's like if you ever take a can of Diet Coke, right? And a can of regular Coke and put it in water, one sinks, one floats. Yeah. It's a good party trick. Yeah. Which one floats? Which one do you think floats? That Coke or regular Coke? Diet Coke floats. Yeah. It's got artificial sweetener in it, right? Regular Coke's got mix at the bottom. Good little party trick. Fun. Fun time. That the Diet Coke floats. That's it's important stuff. When you get to Chem 1B, they're gonna go like, hey, what happens with the Diet Coke and the Coke? You need to know just the water one for sure. Yeah, and that's definitely one that's they definitely want you to know the liquid water, and it's usually just for normal problem solving. Sometimes you do need to use that a number of density of water, and a lot of times it's not given to you in the problem. They just kind of assume you're going to use sort of that number. Here's some other examples as well there. All right, let's try this one here. A student needs 150 cubic centimeters of salt in an experiment. The density of salt is 2.16 grams per cubic centimeter. How many 1 pound boxes of salt would they need? So take a moment there and try to figure it out. Again, you should know the conversion between pounds and grams. Okay, so again here, we pull out the information, which is always a good idea. We have a volume that's 150 cubic centimeters. We have a density that is 2.16 grams per cubic centimeter. So clearly, obviously, we're using density here, which is our mass over volume. I have density, I have volume. So, it would make sense to perhaps go after the mass, which is typically grams, is typically the units that we associate with that. Mass would be volume times density. Now, earlier I said dimensional analysis can be really helpful in a lot of situations, and some of the situations are maybe you can't remember that formula, maybe you just had like a brain fart or whatever they call it these days, and you just can't remember it. You're not sure if you're going to rearrange it correctly or anything like that. You could take a more dimensional analysis approach here. Not even really has to worry about the formula, not even has to worry about rearranging the formula correctly, or worry about am I multiplying correctly or dividing or what I should be doing. So what we could do when we have something like the density is we could think of it as like a conversion factor, which means just like any conversion factor, we could use it with 2.16 grams per cubic centimeter, or we could flip it around and use it in this fashion, since we have kind of a fraction basically that we could use as a conversion factor. So without even worrying about this, which obviously if you want to, you could just plug and chug into that formula if you're confident and rearranged it. I could start with my 150 cubic centimeters, which I know I don't want because I want to end up with a mass or a grams basically. And that's what I want to get rid of. So again, just thinking about dimensional analysis this way, cubic centimeters are on top, so I could just use it like that. Put it in the opposite location. And now for the math part of it, because I took a dimensional analysis approach, I already know the math that I need to do, which is we always multiply the top and we always divide the bottom. So I don't even have to worry about, did I rearrange it correctly? Should I be multiplying or dividing? This tells me right away I should just be multiplying in this case. And that's going to get rid of the cubic centimeters, which will end up with 324 grams here of salt. In terms of significant figures, since we should look at that, we do have to look at the density value here. And basically this is a 1, so we don't have to worry about that number. But this has 3 significant figures. Our original value has 2 significant figures, which means in terms of significant figures, we actually should end up there, which is about 320 grams of salt. First off, any questions on that? And obviously that is what you get here, but if you can't remember it or you're not 100% confident, you can again just take a dimensional analysis approach and you don't have to worry about the formula or rearranging it correctly. By the way, the other important thing is you do want to make sure that you actually answer the question that's being asked, and the question that's really being asked is how many 1 pound boxes you need, right? And in this case, since the pound is 453.6, I only need 1, right? And I'll be in good shape, a little left over. I could sell it to somebody else in the class. Any questions on that there? So again, that is also a really added benefit of just trying to setting things up in dimensional analysis approach. Again, later on when we get into other formulas, you may not even have to worry about the formula and just kind of try to take a dimensional analysis approach. As long as you can figure out kind of what units you need and which ones you got to get rid of, and you're able to kind of do it that way. Any questions? All right. All right. That is it for chapter 2. Okay, so like I said, we're going to go ahead here to chapter 10, which is about energy. So we're going to talk about different types of energy. You're going to talk about some energy calculations, some common units of energy, and we'll talk about mainly specific heat as well. So when we talk about energy, really what we talk about in terms of energy is one of those sort of laws of conservation, and that's the law of conservation of energy, which, as we'll talk about, basically means that there is no creating or destroying energy. It can be sort of transformed into one form or another. It could also be transferred from one place to the next. And this is a part of chemistry which is sometimes referred to as thermodynamics, which you'll talk in more depth in 1A about thermodynamics and energy. When you get to 1B, you'll talk about some other thermodynamic properties and stuff like that. But one of the key things about sort of thermodynamics is we think about kind of two things. We think about the system and we think about the surroundings. And the system is really anything that you're interested in. So, for example, when you are doing an experiment in a beaker, your system is the beaker. Everything outside of the beaker is considered the surroundings, right? So that's sort of the idea here. And what we're going to kind of focus in on in this chapter is that flow of energy from, say, the system to the surroundings, or it can flow in the opposite direction from the surroundings back to the system. So that kind of flow of energy in both directions. And there's really, when we talk about systems, three types of systems that we come across. There is an open system that is something that you can exchange mass and energy with the surroundings. So, for example, that would be like a beaker that is open, which means you could just go right in there and take some of the solution out or whatever out of it, right? So you can take some mass out of it. It is not really well insulated, so it's affected by the surrounding temperature, and it can affect the surrounding temperature. A closed system allows for the transfer of energy, but not mass. And for example, if you had a flask and you put a stopper on it, you would not be able to take anything out of it. So it would then allow you to only look at energy. And you can have an isolated system, which basically doesn't allow the transfer of either, doesn't allow the transfer of mass or energy as well. Here's a couple examples of that. Again, in an open system, things can go in and out. We also have the heat transfer. Put a little stopper on the top, prevents things from exiting or entering, but you can still have that sort of heat transfer. And then if you have kind of like an isolated cooler, if you will, right? It's going to be well insulated from the outside, right? And it is not going to allow anything to come out of, especially obviously if it's a sealed sort of chamber or something like that. It won't allow any exchange of it. Now, energy is really the capacity to do work. And since energy can be measured as work done, it is the force times the distance. Chemical energy, for example, is the energy that's stored within the structural units of chemical substances. So, for example, when we have a substance that has bonds, there's energy associated with those bonds. So, if you have something that actually has bonds, there's a certain amount of energy sort of stored within those bonds. So, for example, if I wanted to break those bonds, would I have to put energy in to do that or remove energy to break those bonds, you think? Yeah, we would have to put energy in. So if you think about it, you got a bond like this, and when you put energy in, everybody gains energy. They could kind of wiggle away from each other. They have a lot more energy. They're able to kind of break away from each other. So you would have to kind of put energy in, which is endothermic, energy absorbed, to break bonds. The opposite is true when you make bonds. It's actually an exothermic process, which means energy is released. And that's same idea. If you got things moving around with a lot of energy, they're not going to want to kind of come together, right? Because they're all bouncing around basically. So As you remove the energy, they kind of slow up, and that allows them to kind of come together there and bond with each other. Exactly, probably how it doesn't happen, but sort of that finger move. But that's how they come together. Yeah. Yeah, so like potential energy, which is the next one on there, there's potential energy kind of stored within those bonds, right? Um, and when you make bonds, there's a certain amount of energy stored with when they come together that can be released. So potential energy is stored energy and is based on its relative position. And for example, the classic example, right, is the giant boulder on the cliff that's going to fall, right? It has a certain amount of potential energy based on its position. And when it does go over, some of that potential energy gets transferred into kinetic energy, right, which is the energy of motion, which, by the way, when it hits the ground, hopefully nobody's underneath it at that point. We won't draw the stick figure there because that doesn't seem nice. But when it does hit the ground, it is also going to transfer energy to the ground, right? And it's going to pick up that energy as well. So it's not going to go anywhere, the energy, in a sense. There will be energy that has been transferred from one point to the next. And now that boulder on the bottom has less potential energy than it did to begin with because it kind of lost some along the way and transferred it to other things. Not really lost it, but kind of transferred some of that energy to other places. Um, and that's the idea here of the law of conservation of energy. Energy cannot be created nor destroyed, but it can definitely be transferred from one place to the next. So the idea when we sort of think about system and surroundings is we sort of think about a perfect transfer of energy. So what that means is if somebody is going to release, say, 50 joules of energy, somebody else will gain basically 50 joules of energy. So there's sort of this nice little perfect transfer of energy from one place to the next. So for example, if you just think about it, we lit a Bunsen burner the other day, right? And when you do that, that's an exothermic sort of process. You could feel the energy coming off, right? You could feel the heat if you got close to the flame. So all that energy that Bunsen burner is releasing is ended up in this case in the surrounding, right? The surrounding air and whatever's near it. The energy that's being released on your beaker that you were boiling, right, is going to be end up into that beaker of water. So in terms of the Bunsen burner, it's an exothermic release of energy. And when you have it underneath your beaker of water, it is the water that's the recipient, right? An endothermic process, it's absorbing all that energy that is coming from the flame. So there's always sort of this perfect exchange of energy. And you may think to yourself, well, if there's perfect exchange of energy, how do we know if something is sort of going to release energy or gain energy if it's sort of the same number, right? And in chemistry and with energy, we actually use signs to help us represent, is this process sort of an exothermic process going to release energy, or is this an endothermic process that's going to absorb energy? And as we will see here and talk a little bit more about as we continue on, our exothermic, which is a release of energy, typically ends up as a negative number. So if you see a negative energy number associated with a process, that usually indicates that that process is an exothermic process. It is going to be releasing that amount of energy. And that is opposite of endothermic process, which is a process where we absorb energy. And typically speaking, endothermic processes are positive numbers. So if you see a positive number associated with energy and a process, you can feel very confident that that is a process where it's going to be endothermic in that situation and they're absorbing that amount of energy. So really, really important. We'll talk about throughout this chapter, especially when you're dealing with energy. energy calculations, the sign is actually really, really important. Is it whether it's a positive number or a negative number, because it does tell people whether or not it is a exothermic process or an endothermic process. So sometimes people, when they do some of these energy calculations, because a lot of them is just like kind of take the difference of the numbers and stuff like that, they oftentimes will do it always like in a positive sort of value way to get a positive number. But it's really, really important when you're doing any type of energy calculation that you do the calculation correct. And when you do the calculation correct, it will actually sort of sort out the sign for you. It'll give you a negative number if you need one. It'll give you a positive number if it should be positive. So you want to kind of keep that in mind in this chapter. The sign is really important in terms of the values that you get. Any questions on that there? So as I mentioned before, what we're really talking about here is what is sometimes referred to as thermodynamics. And in terms of energy, and the first law of thermodynamics is that conservation of energy. So that one we just saw there where energy cannot be created nor destroyed is sometimes referred to as the first law of thermodynamics. You won't see the other laws until you get to 1B, the second law of thermodynamics and all that, but with entropy. But one of the things that thermodynamics oftentimes deals with outside of the energy component is whether or not, for example, a reaction will take place. And that is something that you deal a lot with in 1B when you talk about whether or not a reaction is spontaneous or not. And by the way, just a preview of that, if somebody says a reaction is spontaneous, people oftentimes have a wrong idea about what that means. People think spontaneous reaction means you snap your fingers and it happens really, really quickly. And in the realm of thermodynamics, when somebody says a reaction is spontaneous, it really has nothing to do with how fast or slow a reaction takes place. It actually just means that under those particular conditions, that reaction should take place. And it could take place really fast, it could take place really, really slow. For example, the production of ammonia is a spontaneous reaction. But if you do not use a catalyst, you'll be there all day. It's a very, very slow reaction. So just keep that in mind as you go through thermodynamics. We won't deal too much with that, obviously, in this class, but later on, that's a very common mistake people hear when they think about the word spontaneous. All right, so back to state functions. State functions of a property is really determined by, frankly, two things. Where you started and where you ended. Those are really the only two important things along the way in a state function. So energy is a state function. Things like pressure, volume, and temperature are also state functions. So what does that mean? If we take a look at these hikers here and we take a look at the blue hiker, he took the more direct route up the mountain. The red hiker path took the more scenic route up the mountain. But in terms of their potential energy at this point, they both ended at the same spot and they both started at the same spot, which means when you take the difference of where they ended and where they started, they have the same potential energy. So that's also something that's really important to keep in mind in terms of chemistry, which is not all reactions happen in like a one-step process. There's a lot of reactions that happen in like multiple individual small little reactions that when you add them up together gets you to the end reaction. So that's why the guy taking the scenic route doesn't really matter how he got there. It only matters where he ends up. And one of the important things when we think about something like energy, our energy in general, we oftentimes, this is delta, and delta means the change. So when you see a little delta symbol in this aspect, it means the change of something. It's the final state minus the initial state, just like our volume, final volume minus initial, temperature, final minus initial. Now, one of the downsides of skipping from chapter 3 to chapter 10 is the book assumes that you've already done the previous chapters, which would kind of make sense. So let's just talk a little bit about chemical equations and sort of important parts of it, because that'll be very helpful in this chapter as well. So one way that we can represent a chemical reaction is through a chemical equation. And when we look at a chemical equation, there's usually an arrow, and to the left of the arrow, those are your reactants. And those are your starting material in a chemical reaction. What they form on the other side of the arrow are products. And that is what is basically formed. So for example, if you took, speaking of ammonia, H2 plus N2 makes a little NH3. Bless you. Do a little balancing there. This is a chemical equation. The H2 and N2, which is hydrogen gas and nitrogen gas, are reactants. And our NH3, which is ammonia, is our products here. So in a chemical reaction, if you just think about the equation, where we end up and our final state is our products. And where we began is basically our reactants. So that's kind of like our final state and our initial state. So this is like our final state, and this is our initial state. And that is why in a lot of energy calculations that we will look at in this chapter, are just in general, a lot of times what you do is you take your product's energy and you subtract it from your reactants energy. So products where you end up minus your reactants energy where you started. And that's why we oftentimes calculate energy in that fashion, is because in a chemical reaction, that's essentially the idea there. We have products where we end up, reactants where we start, energy being a state function. That is really what we're looking at. And that doesn't matter if there's like 400 individual reactions, probably won't have that, but a bunch of individual reactions in between. The end result is you could take all of those reactions together, add them all together, you will end up with an overall reaction. And that overall reaction will have a certain number of reactants and a certain number of products. And even though it took like 9 steps to get there, ultimately what's happening is those reactants are going to those products. And then we take that overall reaction, products minus reactants, and that will give us really the change in energy. Any question on that there? Question. So let's talk a little about units and some important units here. The SI unit for energy is actually a Newton meter, and it is also sometimes referred to as a kilogram meter squared over second squared. Most commonly, though, we do use units of joules, and this is not negative, that's just from PowerPoint. So 1 joule is actually equal to a kilogram meter squared second squared. That's actually, I would say, something that you should probably put in the memory bank. Not so much for our class, but as you go through the other classes, that is like a conversion that does pop up a lot for yourselves. We typically will use units of joules or kilojoules are common energy units that we use. And that is the relation here, again, not negative. 1 kilojoule is 1,000 joules. So that's the same kilo conversion we talked about earlier in chapter 2. Definitely should know that because it does definitely pop up a lot. So I would say probably 9 times out of 10, maybe in this school here, in the classes you take, probably a little bit more than that, probably 99 times out of 100, you're going to probably roll with either joules or kilojoules as your energy sort of unit. But there is also some other units that are commonly used for energy. And a calorie, a lowercase calorie, lowercase c, is another unit that is very commonly used for energy. And that is the amount of energy or heat that's required to raise the temperature of 1 gram of water by 1 degree Celsius. Once again, not negative here. So 1 calorie. That is also definitely something you should know. It will pop up here as well in this class for sure, that conversion. That 4.184 number, just put it in the memory bank. It will definitely pop up in this chapter a lot, and we'll see it a little bit later. So like joules or kilojoules, calories or kilocalories are very common units of energy that we come across in chemistry. So the reason that calorie is lowercase is it is different than a capital C calorie. So 1 little calorie is equal to 1,000 kilocalories. I'm sorry, I got that backwards. Hang on a sec here. That's not what I was going to write. Oh, what was I going to write? Sorry about that. I guess what I was going to say, lowercase calorie is different than a capital calorie. This is sometimes referred to as a nutritional calorie. That's what I was trying to write there. 1 capital calorie is equal to 1 kilocalorie, which is equal to 1,000 of the little calories. And so if you have a capital C, that's a nutritional calorie, which is actually 1,000 of the little calories. So we deal with mostly the little calories here in chemistry, if you deal with calories at all. Nutritional calories, you see, like, on treadmills and stuff like that, they'll sometimes even tell you how many kilocalories that you are burning, and nutritional calories as well. One of the way that we use energy is to change the temperature of a substance, ice to liquid water. So if somebody is gaining energy, which is, as we talked a little bit about here, and we'll talk more about, endothermic, will their temperature go up or will their temperature go down if they're gaining energy? Yeah, if something is absorbing energy in an endothermic process for themselves, you should see their temperature rise, right? So that's a reflection of it gaining energy. So their temperature should go up. And obviously, if something loses energy, I guess, releases energy, we'll put it that way, which is an exothermic, their temperature should end up going down. And it is actually that temperature change, as I was talking about a second ago, when we talk about, a negative number for exothermic or a positive number for endothermic. It's actually that temperature change in most cases that turns a number into like a positive number or a negative number, right? So if I have something that their temperature is going up and I do a change in temperature, for example, which is our final temperature minus my initial. If I do it for this situation where the temperature goes up, that means I'm going to take a larger number minus a smaller number, right? Because my final temperature is going to be bigger than my initial. And that's going to give me a positive number, which is going to end up being, for the energy and heat, going to be a positive number. If I have this situation happening, my final temperature is actually going to be smaller than my initial temperature. So when I do the change in temperature, I will have a small number minus a larger number. And typically, if you take a smaller number minus a larger number, you end up with a negative value. And it's really that change in temperature a lot of times that helps determine, what is happening in a reaction or a situation. Is it gaining energy or losing energy? Any questions on that there? Yeah, I think it's probably a good place to lay it up, I think, for today.